Okay. Thank you, thank you. Hello, everyone. I'm Tianyu Li. I am co-founder and CEO of Archon Robotics. We are actually a new startup in Shanghai, China. And I am also a PhD researcher in OpenDrive Lab, University of Hong Kong. So today I want to introduce how do we scaling whole body humanoid skills with human demonstration. So here is the whole outline. I will first introduce a background and also two work of our groups. And yeah, the final part is the next step to the whole body intelligence of humanoid robots. So actually we can see that the humanoid can now like dance, run, and do a lot of cool stuff. Actually, this demonstration shows that impressive control and agility and balance ability. But actually, most of the skills are carefully tuned or trained for a very natural motion distribution. So the harder question is whether humanoids can actually learn multiple skills and generalize to everyday tasks. So, so here is a new area called local manipulation. So basically, local manipulation systems is you can use a humanoid robots to do a lot of manipulation tasks, and you can actually move around anywhere. So compared to the fixed-based manipulation systems, actually the task distribution is bounded by its reach range. But for a humanoid robot, it actually can walk to anything and manipulate any object you see. So the local manipulation demands a very broader generalization because actually the mobility exposes the robot to a far wider distribution of environments, location, object, and tasks. So we can see some demo video from Figure can do a lot of local manipulation tasks with incredible whole body intelligence. So if we want to learn a model to control the robot to do such whole body intelligence or local manipulation tasks, you definitely need a lot of data. And the data should be very generalized to the wild environments. So basically, we cannot like teleoperate the robot to collect all of the data. So that's why we definitely need to learn from the human demonstration. So nowadays, we actually have a lot of human demonstration. We always call it about egocentric data. So we have a lot of egocentric data like Ego 4D, Ego XO 4D, and also Ego DEX. They have the Ego video from our first person views, and also a lot of some of the data set have the annotation of our hand poses. But there are quite incredible data sets, but basically none of them have the pose of our whole body human motion. So actually there is multiple levels of the information in the egocentric data. So the first level is you only have the ego video. So basically, you can see you can have the task semantics, the visual intent, and actually the structure of your action of yourself in the RGB video. And the next level of the ego centric data is you have the E pose, which is an effector pose. Maybe it's your hand or your wrist, or maybe you can have a gripper, some kind of umi things. So you can have the trajectory of your manipulation skills, and also you can do the task. You can obtain the action of your task space. But in this data, you cannot have any of your lower body motion because you cannot see them, definitely. And for now, we think the highest level of ego data is we call ego body data, which you can have the ego-centric view of RGB image, and also we can record your whole body pose. So then you can learn a lot of whole body intelligence from the human data, including the weight shift, stepping, and leaning, kneeling, a lot of whole body coordination action. So definitely the data scales. The most scalable data is Ego video only. You only need an iPhone or a head camera to capture all things. So, but also body super region determines like the what we can learn from the human data to the robot. So this is a line of our work. This is a preliminary work called WholebodyVLA. In the last year, iClear 2026, we actually learned to how to pre-train from the egocentric human video, which is the level 1 part. So the VRA framework, everybody is familiar with that. Basically, you have a VRM backbone, and it can read the image observation and also the task instruction. And then it output maybe robot joints or any factor pose to do a lot of manipulation tasks. So for humanoid, there is actually a very simple and direct humanoid VRA pipeline, which is you still have a VRA and it's outputs the manipulation task for the upper body, and also is have additional branch to output some locomotion command or sparse command, which is going forward, going backward, turn left, turn right, squat, stand up, something like that. And then you can train a very robust low-level controller to accept these commands and keep balance when your upper body is doing manipulation tasks. So basically, we call this is the combined paradigm with a high-level planner of upper body and a low-level controller for the lower body. But the thing is, because all of the existing VRAs are pre-training in the manipulation tasks. So we have actually a lot of manipulation data sets. One of this is AgiBot World, maybe millions clips of tabletop manipulation in this data set. Also, we have a lot of navigation data sets, but we found that the manipulation and navigation are basically separate tasks. So it's very hard for the robots. If we only learn from these data, they cannot learn how to reaching while you are moving. So we did some very simple things. We just let our data collector have a head camera on it and collect a lot of manipulation aware locomotion data. So basically, you want to manipulate any objects, and also you are walking around. So combine these locomotion egocentric videos and manipulation videos existing in the community, we can pre-train a latent action model following the LARPA paradigm, and you will have a very good visual encoder, and you can pre-train a code book for all of your latent action. And then you can put these latents into your VRAs, and the VRAs can learn what local manipulation task is, and then you can decode all of the action out, including the upper body and the lower body. So in this paradigm, we can actually do a lot of things for the humanoids. This is some demos. We can see actually it can do a lot of move and manipulation tasks, and it can carry things. It can carry things and move around, and also it can do a lot of manipulation, long horizon things. So in these tasks, the robot learns how to move from the local manipulation videos, and also learn how to manipulation from the egocentric videos. Yeah, this is also list of the work. Thanks all of the authors for the incredible work. So let's go to the next step. How do we learn more from the egocentric video, which is the level 2 of our ego data set? So this is a work called Humanoid, EgoHumanoid. It's actually in a different things. In WholebodyVLA, we are doing human data pre-training using LARPA, and then we do post-training with robot data. So in this work, we actually explore human-robot co-training for the post-training stage. We actually collect a lot of in the wild human data with the whole body pose, and we collect robot data with teleoperation system, and then we co-training them together in the post-training stage, and we found that the robots can actually deploy in the wild environments and do all of the local manipulation tasks. So how do we collect those data? We actually design a very simple and scalable data collection system. We use a VR headset called Pico 4 Ultra. This headset is have some Pico motion trackers. So in the left part, we use the a Pico 4 headset to teleoperate the robot. So then we can have record of the robot pose, of their arms, of their hand grabs. So basically, you can have some 7 DOF actions from your robot upper body, and then we can record a lot of the local motion command for your lower body, which is your leg. And the right part is the human. The human data. Human data is we collected using the VR headset, but we mount a same camera, same as the robots on the headset, and then we can have an egocentric video, and also we can have the hand pose from the egocentric video, and also because we have the Pico tracker, is we can have the whole body pose of the human. So the whole price of the whole device is around $1,000 US dollar, so it's super cheap and it can scalable. So we collect a lot of these data. So first is robot data in the laboratory, because when we tally up the humanoid robots, it can only working with some workstations or with a lot of wires. It cannot connect outside. So here we have 4 tasks: cart stowing, toy transfer, trash disposal, and pillow placement. And also we can easily collect a lot of diverse human data. We can actually put our data collector into the supermarket, into the apartment, outside, in the park, something like that. We can collect a lot of data with same tasks. So in the human data collection, basically we can collect a lot of things like 24 DOF whole body pose and also hand pose from our device. And the thing is, clearly there is a gap between human and robot. So basically the human is very tall. Our data collector is around 1.8 meter high, and the Unitree G1 robot is only 1.3 meter high. So the visual gap is one thing, and another thing is the action representation. We are human, so this is human skeletal, and also the hand pose is totally different with the robot arm. So we do 2 things. So first, it's actually very heuristic. We use a depth model to predict all of the depths and project into 3D space, and then do imprinting to fix the hole because of the occlusion or something like that. So basically, we can transfer the viewpoint from human to robot height, and then we align the action space of human to robot. So basically, for the upper body of the human, we can calculate the end effector pose of the human hand, and the lower body pose, we just quantize them to discrete velocities of the locomotion commands, and then we transfer the hand pose to a binary open and close signal. So then we found that okay, the visual gap and the action gap from human to robot is kind of bridged by this pipeline. So, and then we simply co-train the human data and robot data. And we found that is surprisingly very work, especially in the generalization performance on the right table. So the green one is co-training robot with human data, and the red one is robot data only. So in this setting, we found that the co-training is actually very worked to increase a lot of success rate, especially in the unseen environment which robot can see. So also there are some ablations. The view alignment is super work. Like after we project it, there are a lot of backhoe due to occlusion or unseen area. And after the fix looks like very real. And also the view alignment works a little bit in the final success rate. So this is my favorite demo here. It's actually a fully zero-shot deployment. The robot and the human never collect data in this scene. It's actually a Bay Area in Shenzhen, Shanghai, and the robot can definitely put the trash can here, and the robot can just walk to the trash can and throw the trash into it. So it's actually show a lot of generalizability for the robot when it runs from human videos. So this is the author list of the EgoHumanoid thanks to the authors also. So this is actually another also a RSS accepted paper. So I think the Dr. Shi will also introduce the work in the next few days. And the last part, so the road to whole-body intelligence. So I think you both of you find that we actually all the WholebodyVLA and also the humanoid, they are actually a combination of the upper body manipulation and the lower body commands. But we found a lot of very incredible skills, especially in the figure demo. The robot can actually shift base while pulling dish rack and for the dishwasher. And also it can use the foot as an additional hand to close the dishwasher. So these tasks cannot be achieved by a combination of upper body and lower body. So the locomotion manipulation is definitely not simple locomotion plus manipulation. We actually definitely need some whole body coordination or whole body intelligence. So in our past, the WholebodyVLA learned from egocentric video only, the EgoHumanoid additionally learn from the anti-factor pose of the human data. And the final step or the next step should be we can have some kind of the humanoid foundation model. It can preserve all of the strategy from the whole body motion trajectory. And it should output the robot motion trajectory by human robot data co-training or robot grounding. So the missing piece is actually here is always whole intelligence. We found that definitely we can have the data pre-train and we can train the humanoid foundation model. And the third part is that we definitely need some controller run at very high frequency and track the robot motion trajectory to control the humanoid robots. So fortunately, we have some very good work here. So like Twist 2, Sonic, and Agility meets Stability. This is actually our work. You can see that the robot can actually mimic a human doing and to do a lot of manipulation tasks. But now all of the universal tracker is tracking a human motion or tracking a human teleoperator, and it's very weak when the humanoid do a lot of the crazy things like lift a very heavy stuff, because nowadays the universal tracker is very hard to adapt it to force and task and also high precision manipulation. So this is what we are doing, and we are working here in Arcan Robotics, our startup. We actually have some um, preliminary results. Like you can see, our robot can lift a very heavy object, which is a falling bicycle, and also it can do some intelligence navigation, like it can pass a very narrow walkway of your kitchen, and also it can kneel down and pick up a very cute beer. So this is basically what we think in the future the humanoid can do a lot of tasks in your home or anywhere in our daily life. Okay, thank you. This is all my tasks.
All right, thank you for the present. Any questions from this floor? Yes. Yes, please.
I think one of the problems that occurred with human demonstrations is kind of like we are sometimes forced to act like a robot ourselves in order to simplify the gap.
Yeah.
There are methods that you are thinking of using to avoid that or to learn from more human-like behaviors instead of having to precisely like act like a robot.
Yeah, that's a good question. So nowadays, I think humanoid robots do not have a very strong hardware to act as a human. Like, but we are doing that, like to train a better universal tracker, it can actually do more natural and more human-like action today. So if we have a strong enough universal tracker, and also we can have stronger and stronger humanoid hardware. So we can actually have the ability to let the humanoid robot act as human if we can have a humanoid foundation model output the human natural behavior. So in that day, actually now we are letting our robot to do some task like human, like it can step and reaching a very far along very far things on the kitchen. So for these tasks, you actually need your humanoid robot can keep balance and can have the like very strong capability of your especially of your torso on your ankle, and then you can do a lot of very human-like motions. So I think the future is that we have a better hardware, better universal tracker, and the robot can do anything like human can do.
Yeah, each of the tasks, I think, like, you need to collect data samples, right? So what's the maximum, like, data samples for each task to collect? And second question is like, each of the tasks can be solved, I mean, like, can be solved in a different ways, like, each of the tasks have a different, distribution. So how do you model, like, a multimodal distribution? Okay, so.
Okay, cool. So I have two questions. So the first question is about how many data we collect in this each tasks. So in our EgoHumanoid, we actually collect hundreds of thousands of demonstrations for each task, including the human data and also the robot data. So it's basically like one-to-one between the human and robot data. So, but in this amount of data, it can only like it's kind of overfitting to this task only, but it can generalize to the environment because we have a lot of environment in human data. But the second question is how many amount if we continues to scale up the human motion data and also the robot data, can we let the robot learn multitask, and also it can learn from a very like multi-model distribution. Yes. So definitely the humanoid is like the action space of the humanoid robot is more multimodal than simple manipulation. So in pre-training stage, we actually need to keep these multimodal tasks, but we need very good text descriptions. We need a very good ways to let the model learn the multimodal actions. So you have dense text predictions, you have flow matching to model of the multi-modality. And into the post-training stage, we actually need your data collection very stable, very low multimodality. You need to have a very narrow distribution to maximize the success rate. So definitely in today's stage, we still need post-training stage to deal with all the tasks. Thank you.
Let us send the speaker again.